So welcome to this session on gravitational waves. As you know, the last year was a very important year because after 100 years, the discovery of gravitational waves happened. So in this particular session, we have 3 talks. The first talk is by Professor Ajit on the discovery of gravitational waves. Our colleague Unnikrishnan could not make it because of some health reasons. So instead of him, I would give a talk on the detector. And then there will be a third talk on the LIGO India, the research happening around gravitational wave research in India by Sanjeev. Because we have a very packed program, we will take questions towards the end of the session. So we'll have all the 3 presentations and then we will open up the floor for questions. So with that, let me begin with the first talk by Ajit. Ajit is a faculty member at the International Center for Theoretical Sciences. He's the leader of the Astrophysical Relativity group there. His PhD is from the Max Planck Institute for Gravitational Research. He was a postdoctoral fellow there and then at the Caltech in the USA. He's a member of the LIGO Scientific Collaboration since 2004. He is a Ramanujan Fellow and heads the Max Planck Partner Group on Astrophysical Relativity and Gravitational Wave Astronomy at ICTS. Both Ajit and Sanjeev have made very important contributions to the discovery. So you are hearing about the discovery from people who have been involved in it in detail. Ajit.
Good morning, everyone, and thank you very much for coming this morning to listen to us. Today, I'm hoping to tell you the story of the discovery of gravitational waves, which was predicted by Albert Einstein exactly 100 years ago in 1916. And this recent discovery of gravitational waves is important not only because it confirms a century-old prediction of Einstein, but it essentially opens up a new branch of observational astronomy, a new way of observing the universe. So essentially soon after discovery, it captured popular minds all over the world, and it really became part of the popular culture. It even made it to the Amul advertisement. So I saw this billboard in Mysore, which reads, all but Einstein. It shows the popularity of gravitational waves of Einstein again recently. So let me start by showing a few pictures of the universe that we obtain from different branches of electromagnetic astronomy. I suggest that you look at those slides, that projector, because that is better quality. So, of course, if you look at the sky using an optical telescope, you see a familiar picture of the optical sky, the stars, galaxies, and so on. And essentially, it's dominated by our own galaxy, the Milky Way. But if you look at the same sky using a detector that can detect microwave radiation, you get to access to a very different history of the universe. What you see from everywhere in the sky, a cosmic radiation, a radiation coming from a very early universe called the cosmic microwave background radiation. It's shown in this middle panel, this with red and blue regions. So essentially, the radiation comes from an age of the universe when it was very, very young, and it's only about 100,000 years old. And we know that now the universe is about 13 billion years old. So it's a baby picture of the universe. And you see here in this top middle panel some blue regions and red regions. This shows the temperature of the cosmic microwave region of background radiation. And of course, this temperature difference is extremely minute. But this red regions eventually became stars and galaxies, and these blue regions became essentially large intergalactic voids. So similarly, if you look at the sky using an X-ray telescope, you get to see very high energy phenomena involving black holes accreting matter around them, very high energy neutron stars, etc., etc. So it's fair to say that essentially all the information that we gain about the universe mostly come from astronomical observations of electromagnetic waves. But recently, astronomical observations using non-electromagnetic messengers also have become possible. This plot shows the arrival directions of very high energy neutrinos. Neutrinos are subatomic particles that are chargeless and almost massless. This is observed by a fantastic observatory in Antarctica called the Ice Cube. These have very high energies, hundreds of GeVs, and it's not entirely clear what is producing them. This is rather reasonably clear that it is coming from extragalactic sources. And it shows really how a new branch of astronomy opens up new questions. And the neutrinos and electromagnetic waves contain very complementary information. For example, electromagnetic waves are produced by the surface of objects, stars, or their atmosphere, etc., while neutrinos are typically produced in the interior of these objects, in the interior stars due to nuclear reactions, etc. So they essentially contain information contained to very different physics. So by combining this information from multiple messengers, we are able to provide a more complete picture of the astronomical source that we are probing. And finally, I would like to show the first picture of the gravitational wave sky. This is the reconstructed location of the first gravitational wave signal observed by LIGO last year. This is produced by a merger of two binary black holes. Before I come to describing this discovery, let me give you a very brief introduction to what is gravitational waves are. So the existence of gravitational waves was predicted by Einstein's theory called the general theory of relativity, which is already celebrating its 100th anniversary. So this GR, general theory of relativity, is the most accurate description of gravity available to us now. It is much more accurate than the Newton's theory that we all study in school. Essentially, it tells that gravity is nothing but the curvature of space and time. It's a single entity called space-time. So if you have any massive object, like an apple, it curves the space-time around it. So of course, the space-time curvature produced by an apple is extremely small, but if you have a really massive and compact object like a black hole or even the sun, it produces a significant curvature of space-time around it. And of course, very far away from the source of gravity, gravitating source, the curvature is very, very small, so it's a very, very approximately a flat space. So if you, for example, all the usual axioms of Euclidean geometry holds in this flat space. For example, if you draw a triangle and sum the angles, you get 180 degrees. But if you do the same exercise in the vicinity of this massive object, this axioms of Euclidean geometry does not hold. For example, if you draw a triangle and sum up the angles, it will no longer be 180 degrees. So the space-time is truly curved there. And so it might look like a very exotic and prediction, but we are already using the predictions of GR in our daily life. For example, most of us have smartphones and we use GPS to navigate in the streets. So if the GPS has to work, the effect of the curvature of time, the effect of the slowing of time due to the gravity of the Earth has to be taken into account, because essentially GPS uses a system of very precise clocks to essentially locate our position in the three-dimensional space. And the point is that clocks tick at different speeds depending on their gravitational field. So a clock that on the surface of the Earth would tick slower than an identical clock that is on the outer space. And since GPS relies on clocks that are placed on board satellites, essentially one has to take into account this minute change in the flow of time for the GPS to work accurately. And gravitational waves are something more exciting, more exotic, that is predicted by Einstein's theory. Essentially, it tells that, I told you that a massive object curves the space-time around it, and when this massive object moves, the space-time curvature moves with the body. And when this moves with an acceleration, this oscillation in the space-time curvature decouples from the source and propagate outward like ripples in space-time. So gravitational waves are freely propagating oscillations in the fabric of space-time, which is as shown in this animation, which is produced by, which shows a gravitational waves produced by an orbiting binary star system. Now, how do you detect gravitational waves? When gravitational waves pass through the Earth, they produce some very characteristic deformation in the space, the spatial metric. So, for example, if a gravitational wave is passing perpendicular to this board, one direction of space gets stretched and the other direction gets compressed. So it's characteristic of what is called tidal forces. For example, tides of the Earth created by the moon. For example, the Earth has a really fairly spherical shape, and due to the gravity of the Earth, it gets deformed into ellipses. So gravitational waves does something very similar, but except that this deformation is perpendicular to the direction of propagation of this wave. So the space is stretched and compressed in the direction that is orthogonal to the direction of propagation of this motion. It's shown in this nice animation. You can see that if you arrange a ring of particles, a test particle that allows to move freely according to the stretch, strain on the space, if you arrange it in a circle, then the circle gets deformed into ellipses, and this deformation propagates outwards at the speed of light. This is called gravitational waves. And there are different ways of detecting gravitational waves that have been proposed, and the first successful one has been using what is called laser interferometer. So you will hear about this instrument that made this detection of gravitational waves in the following talk by Bala Iyer. But essentially the idea is that uses something called a Michelson interferometer, a very sophisticated Michelson interferometer. So Michelson interferometers have been around for more than a century. It's a very standard technique in physics. But the problem is that the expected change in the space, expected deformation of the space, as well as the expected change in the arm length of this interferometer is extremely tiny. So the fractional change in the length of the space, or the length of an interferometer, is of the order of 10 to the power 21, even for a very loud source, that, for example, like the one that we observed for the first time in LIGO. This means that if you are using even a kilometer scale detector, an interferometer that has a kilometer's arm length, it should be able to detect extremely tiny changes in its arm length of the order of 10 to the minus 18 meter. And that's a huge experimental challenge. And by far, these instruments are the most sensitive measurements for measuring length ever constructed by humankind. And we will hear about this in the following talks. And an international network of such detectors existed in the last 10 years in the US, Europe, and in Japan, etc. And the first generation of these detectors have been conducting a data taking runs over the last 15 years or so at various times. But they were not successful in making detections. But these LIGO detectors in the USA essentially underwent a major upgrade in the last few years to a configuration called Advanced LIGO, which was much more sensitive than the previous generation of LIGO instruments. And as soon as they started operating on the 14th of September 2015, they detected the first gravitational wave signal. In fact, this was actually before the official start of the scientific run. These gravitational waves were waiting for us. So these two signals arrived in these two detectors at a time difference about 7 milliseconds, because they travel at a finite speed, at the speed of light. And the combined signal-to-noise ratio, this is a very loud event. The combined signal-to-noise ratio of this event was of the order of 24. The signal was about 24 times larger than the noise. And these gravitational waves have frequency in the audio frequency band. They have frequencies of the order of 10 hertz to a few kilohertz. This is the frequency where our ears are sensitive. That's why it's audio frequency band. So it's actually possible to convert the observed signal into a sound and play it in a loudspeaker. And I will do that now. I'll show this observed signal, and you can actually listen to this signal. Because the buzz that you heard is the instrumental noise, but you see like a plup and plup. This is the sound of the first gravitational signal that we observed. And this plot shows the observed signal in the two detectors. The horizontal axis is the time. So it's only a fraction of a second. It's of the order of 0.1 second. And the vertical axis shows the amplitude of this oscillation as a function of time. Suddenly these detectors are oscillating as a function of time with this frequency. So you see this characteristic singular shape that we were expecting to observe using, which correspond to the merger of two black holes. And also this shows how the frequency of the signal increases as a function of time. It starts from low frequency, go to very high frequencies. So by the careful study of the observed signal, the collaboration has concluded that this is consistent with a signal expected from the coalescence of two black holes. That is, two black holes formed at some distant galaxy as a binary system. They were orbiting about each other. They lose energy into gravitational waves. And as a result, they come closer and closer. And as a result, they rotate faster and faster. And eventually, this becomes like a runaway process. And these black holes merge to form a common black hole, a common horizon, and which settles into a single rotating black hole. And this is the expected signal from such a phenomena that you can compute by solving Einstein's equations in general relativity, and the observed signal agrees very well with this prediction. So the signal has a very characteristic shape. If you look at the earlier part, it has an increasing amplitude and increasing frequency. Such a signal is called a chirp because the spectral characteristic of this signal is very similar to the chirping of birds. So it's called a chirp signal. And the later part, when these black holes merge, essentially the signal amplitude dies exponentially. So this discovery is what physicists call a 5 sigma discovery, which is like a gold standard for detecting anything new in physics. This means that essentially it's extremely unlikely for anything other than a gravitational wave to produce a signal like this in our detector. The false alarm probability, the probability that something other than a true gravitational wave to produce something like this signal is less than 10 to the minus 7. It's extremely unlikely. So, or in other ways, it's only once in 2 lakh years, 200,000 years, you expect to see something like this produced by noise. So we are pretty short, very extremely certain. We are very confident that this is a true gravitational wave signal. And it actually took a lot of time to establish this with this confidence because, if you remember, the signal was discovered on the 14th of September 2015. So, and the detection was made 3 minutes after the signal arrived in the detector. But this discovery was announced only in February 2016. So in this 5 months, all this 1,000-member collaboration was essentially doing an extremely exhaustive exercise to make sure that this is indeed a gravitational signal. Essentially, thinking of all kinds of possible alternative explanations and ruling them out. So what are the possible explanations, alternative explanations? For example, there are, this detector is operating in our environment. So in principle, various environmental noises such as seismic events or magnetic events, etc., can cause an event in the detector. So in order to make sure that this is not caused by any of the environmental or instrumental noise artifacts, there are essentially thousands of sensors, seismometers, magnetometers, microphones, acoustic sensors, etc., placed around the instrument, as well as the detector is monitored by around thousands of ports. So there was an exhaustive exercise to make sure that this data could not be explained by an event in any of these environmental channels. So we find absolutely no evidence that this could be an instrumental artifact because none of the environmental sensors recorded an instrument and determined that can potentially couple to this gravitational wave event, channel. We also essentially explored the possibility of someone either maliciously injecting something, a signal in the data, and this was also ruled out by a large amount of human exercise. So we are fairly confident, extremely confident that this is a true event. And this is one of the most, in fact, this is the most powerful astronomical source ever observed by a humankind. Because about 3 solar mass worth of energy has been converted into gravitational waves over the course of a fraction of a second. Using a 3 solar mass of energy, an equivalent of 3 solar mass of energy in terms of mc squared is converted into energy and radiated in a fraction of a second. So if you convert the power emission from the source during this merger, it's of the order of 10 to the power 49 watts, which if you imagine, it is 50 times larger than the average luminosity of all the stars in the universe put together. So if this, for example, if this event was converted into, this energy was converted into electromagnetic energy, it would sort of outshine the entire universe. But this was not converted into light. There was no light emission. All this energy was converted into gravitational waves. And because the gravitational waves, gravity couples to matter extremely weakly, even with such a large explosion of energy, this observed signal is extremely feeble. And it takes this huge amount of effort to observe such a signal. So by studying the data, by comparing this data with theoretical predictions of this source by solving Einstein's equations, we conclude that the signal was produced by the merger, the in-spiral and the subsequent merger of two black holes with masses 36 and 29 times the mass of the sun. These are extremely massive black holes. And they merged to produce a single black hole of mass 62 times the mass of the sun, even more massive black hole. It was rapidly rotating, that is rotating with a spin, a dimensional spin, is of the order of 60.667. So they were spinning the 67% to the maximum spin possible in a curved black hole in general relativity. So those who are careful, you might notice that the mass of the final black hole, 62, is smaller than the sum of the initial masses, which should be 65. So this 3 solar mass of mass is converted into energy in this process. And a second signal was detected on the 26th December 2015. This was produced by the merger of a lighter black holes of masses 14 solar mass and 8 solar mass, and they have merged to form a remnant black hole of 21 solar mass and the spin of 0.74. This observed signal is entirely consistent with the prediction of Einstein's theory. So in fact, it's a remarkable test of Einstein's theory. It's the first test of Einstein. This provides the first observational test of Einstein's theory in the highly relativistic regime. So before these black holes merge, they must have been traveling at a speed which is close to the speed of light, something like 0.5 times the speed of light. So this is the first test of, this is the first experimental verification of Einstein's theory in this extremely relativistic regime. So of course, Einstein theory passes the test with flying colors, yes. But of course, at this point, our errors are largely dominated by our statistical errors because we have large uncertainty in measuring parameters, etc. But one of the things that we hope to do using the future observations of gravitational waves is by combining a large number of such observations to make very, very precise constraints on deviations from Einstein's theory, etc. Even this first observation of gravitational waves also has a profound impact of our understanding of astrophysics. For example, this is the first time we are detecting a new class of source, which are a binary system of two black holes. The first time we are seeing such source by any means of astronomy. And in addition, this first event, the black holes involved in this event, this masses about the order of 30 solar mass, were significantly more massive than the mass of black hole that people thought would exist in the universe, the mass of stellar mass black hole, that are black holes produced in the collapse of massive stars. So most of us were believing that the stellar mass black holes would be less massive than of the order of 20 solar mass. So the first time we are seeing stellar mass black holes with mass more than 25 solar masses. And by making use of this observed number of events, in fact, a third less significant event was also discovered in October last year, but we don't call it as a confident detection. So still, by studying this, by making use of this observed rate of gravitational events observed by LIGO, we can make predictions of the rates of compact binary coalescence, the rate of the mergers of binary black hole systems in the local universe. And we expect that by means of this observation, we expect that every gigaparsec cube of the local universe would have of the order of 9 to 240 binary black hole mergers to happen every year. This means that if you continue operating LIGO with improved and improved sensitivity, you will see several more signals in the next few years. And when the LIGO observe in its design sensitivity, you are expecting to see hundreds of binary black hole mergers every year. So this is going to be opening a completely new branch of observational astronomy. So because of this large number of astrophysical sources merging at the same time, we expect what is called a stochastic background of gravitational waves produced by this large number of astrophysical events. And this is something that we are very, very excited about, and we hope to see such a background, a gravitational wave background in the next 5 to 10 years. And Sanjeev here is an expert on detecting such a background. And hopefully we'll talk about more in this a little bit. Okay. So let me conclude this talk by essentially juxtaposing the sky that we have observed in the gravitational wave window on top of this, all these observational windows that existed prior to the LIGO event. So of course, so this is the reconstructed location of the first LIGO event that we reconstruct using the data. And of course, we don't have a very precise location of the source. So we can see that the signal must have come from a large patch in the sky, shown by this colored contours here. And this is because gravitational waves have a very different characteristic. Their detectors work in very different ways. They are very different from a telescope, which you can point to a particular point in the sky. They are essentially antennas that have large antenna patterns. So essentially, if you have one detector, it can basically able to see almost gravitational waves coming from almost everywhere in the sky. So the way we localize the source in the sky is by combining the data from multiple detectors that are geographically separated, by looking at the time of difference in the time of arrival of the signal at multiple geographically separated detectors. So the accuracy with which we can localize the source depends on the baseline of this international network, how far these individual detectors are located. And with this current LIGO detectors, the accuracy is not that good. So we are expecting to see several new detectors coming up in the next few years, but most importantly, we are expecting the LIGO India will come online in the next 10 years or by 2024 or so. And this detector is located at a significant difference from all these existing detectors, which will significantly improve the accuracy with which we can localize sources in the sky. And this is very important because we also want to see if this merger process, like the merger of neutron stars, etc., produce some electromagnetic counterparts also. Because if you want to do multi-messenger astronomy, you want to observe the same source using multiple means of astronomy. And LIGO India will be, in some sense, really the facilitator of multi-messenger astronomy using gravitational observation. And we will have a whole talk by Sanjit Mitra at the end of the session on LIGO India and the capability of the Indian detector for the future of gravitational astronomy. So I will stop by flashing a quote from Kip Thorne, who gave a plenary talk in the first day of the Science Congress. He was one of the founders of LIGO. So Kip Thorne says that with this discovery, we humans are embarking on a marvelous new quest, the quest to explore the vast side of the universe. So thank you very much. So I guess we will take questions at the end of the... Can you hear me at the back? So my talk would be about the instrument which made this discovery. So this instrument is called Advanced LIGO, and LIGO stands for Laser Interferometer Gravitational Wave Observatory. So just to remind you, gravitational waves, as Ajit told you, are freely propagating oscillations of the gravitational field, and physically gravity manifests itself as a tidal effect. So you can say that gravitational waves are oscillating tidal gravitational fields which propagate out from the source. So if you ask for the properties of gravitational waves in general relativity, one can show that this tidal force field looks like either a plus or a cross, and therefore if a gravitational wave is incident
normally on a ring of particles. It will be tidally stretched and squeezed in an oscillatory time-dependent manner. So if you want to detect gravitational waves, you really have to measure this amount of squeeze, and to quantify it, you introduce a notion called a gravity wave strain. If you take two test particles and separate it by a distance L, if a gravity wave signal squeezes it by a separation delta L, you take the ratio of delta L by L. As Ajit mentioned, gravitational waves were predicted by Einstein in 1916 as an important consequence of general relativity. He gave what is called as the quadrupole formula, using which one can estimate that if you have a lab source, the strain it produces is of the order of 10 raised to minus 39. It is very, very feeble. And that's the reason Einstein himself realized that this has practically a vanishing value in all conceivable situations. Ripples would be vanishingly small and nearly impossible to detect. However, by 1957, in an important conference which is called the Chapel Hill Conference, by the work of people like Felix Perani and Hermann Bondi, the fact that gravitational waves are physical, this issue was resolved, and in a sense, the quest for gravitational wave detection was really born. Because Perani pointed out that the tidal effect of gravitational waves are unambiguous. Mathematically, they can be calculated by using the geodesic deviation equation, and this led Weber to build his first generation of detectors, which are called bar detectors. However, to get to the present generation of detectors, it was almost 50 years, and in between, we had access to new technology, new sources, new understanding of sources, new computing resources, and essentially 3 generations of physicists who worked on this particular problem. So if you had a binary neutron SAS system instead of a lab source, then if you put such a system in the nearest cluster of galaxies, which is like the Virgo cluster of galaxies, you have a strain which is more reasonable, a strain of the order of 10 raised to minus 21. So if you can build an interferometer which is of an order of a kilometer, you have to measure a displacement which is 10 raised to minus 18 meter. So if you really want to detect gravitational waves, you really should be able to measure a very small strain and the associated displacement. Remember, the displacement is 1,000 times smaller than the size of a nucleus. If you build a bigger detector, then the displacement is larger, so that is the reason we build large interferometers. And if you compare with the technology required, the Michelson-Morley experiment of special relativity essentially measures a displacement of only 10 raised to minus 9 meters. So you really needed to improve technology by 10 orders of magnitude. The story of LIGO essentially begins with 3 important documents, one of which is called the RLE paper of Ray Weiss, who basically talked about the feasibility of using laser interferometers to detect gravitational waves, and more importantly, he tried to understand all the other noise sources which we should fight against. Then there was another document which is called as the Blue Book by the community, and finally in 1989, the first proposal for LIGO construction was really made. These are the people in some sense who were behind this endeavor, and I basically show this picture to show you that when they began, they were young people like Ajit, but by the time gravity waves were discovered, they are older like me. So it essentially involved many generations of detectors, and the other person who brought in technology was Ron Drever. The project really requires support by the funding agency, and at the funding agency there was a colleague called Richard Isaacson who essentially made sure that this long haul project was sort of funded. The project needed to be approved. This was done by Rob Vo. And finally, Barry Barish put together the technology and the working practices of the high energy physics community and built what is called as the LIGO scientific collaboration. So what I'm going to talk about is the work and the outcome of the LIGO scientific collaboration. So let me remind you of what is laser interferometry. A laser interferometer is basically an instrument, a most sensitive instrument to measure small displacement. What is shown here is what happens in an interferometer. The light gets split, goes to 2 mirrors, and then comes back. But it is shown a little more detail here. If the 2 arms of the interferometer are of equal length, then the light goes to the end mirrors, comes back, and because of the fact that the length is the same, there is destructive interference, and at the output there is no light which comes out. Because of the gravitational waves, if the mirrors are moved in a tidal manner, then some light leaks out, and what you try to do is monitor the light which comes out of the photodiode. So this essentially is the basic principle by which you try to detect gravitational waves. So one can say that the mirrors are acting like test masses. The passage of gravitational waves induces differential arm length change, which is proportional to the gravity wave strain amplitude. This generates power fluctuations in the output port, which are measured by photodiodes. A simple Michelson interferometer, a few kilometers long, is what is shown here, but it is not sensitive enough to detect the small changes we want to do. So what you do is try to increase the optical path length by using a Fabry-Perot cavity and making the light bounce many, many times. So it essentially increases the path length by about 100. Because all the light which comes out, because you're putting the instrument at this dark port, there is all the power is coming back to the laser. The sensing which you can do of the fringe can be made more accurate if there is more power in the laser interferometer. So you do what is called as power recycling. And finally, to improve the interferometer response, you do what is called as signal recycling. So at the end of the day, you can say that with the technology we have today, you can not just measure fringe width, you can measure 10 by 10 raised to minus 11th of a fringe, and that is essentially what allows us to detect gravitational waves. In a sense, you can say the interferometer is acting like a transducer which converts the gravitational wave to a photocurrent which is proportional to the strain amplitude. But the point is that you can't have this interferometer clamped to the laboratory because you want the mirrors to move. So it is a more complicated kind of interferometry involving freely falling masses. But as I told you, there are a lot other noises which the interferometer is subject to, and basically therefore you really have to understand and control all those sources of noises. So the basic message is the response of the interferometer to the displacement depends on the frequency in which you are operating the interferometer, and the masses should be made free from all kinds of environmental disturbances if you want to build a sensitive interferometer. And this essentially was done by the LIGO project, and because we are trying to measure something very, very feeble, you won't believe it if you see the signal only in one particular interferometer. So the LIGO project essentially consists of two facilities, one at Hanford and one at Livingston. To be even more serious, even in the Hanford beam tube, you actually put in two laser interferometers. This is important because it is one of these interferometers which will come to India to create LIGO India. So what you really are trying to do is making sure that if you see an astrophysical signal only in one of them, you would not believe it. You would like to see the signal also in the other interferometer. And because you want to do that, you essentially align these two interferometers so that you can definitely see the signals if it's an astrophysical one. So this is the Hanford interferometer, 4 kilometers long, the Livingston interferometer, which is again a clone of that same one, and finally in Europe also there is a large scale interferometer which is called Virgo, which is about 3 kilometers long. These are the people who essentially brought this particular project into being in Europe. Now what are the keys which allowed us to go to the advanced instrument? So as I told you, you really need to beat a number of fundamental and technical noises that affect the measurement at this subnuclear length scales. For example, if you want to be sensitive at high frequencies, you use high laser power. If you want to be sensitive at the mid frequencies, you use, for example, lower thermal noise mirrors. And the most biggest challenge is that at lower frequencies, there is a lot of seismic noise, so you really need high quality seismic isolation systems. So the important point is that this project really involves instrumentation science at the frontiers of physics fundamental limits. This is, for example, some subsystems of it, the laser, which is really a 200 watt single frequency, single mode ND-ARC laser. The challenging requirements because you need frequency sensitivities of this particular order, amplitude sensitivity of this particular order. So you would see that in every slide which I am showing you, the requirements are at the limits of technology. This is the crown jewel, the test mass, which is made up of ultra high purity fused silica. It's a 34 centimeter diameter, 20 centimeter thick, 40 kg in weight. And if you look at its requirements, it has to be flat up to lambda by 1000. The coating uniformity should be about 0.1 nanometers. It should have absorption which is very, very small, less than 1 part in a million. Scattering again very, very challenging. So you would see again that the technologies are very, very different things, but everywhere you are at its limits. The other thing, as I told you, is you should have to isolate the system from all the other noises. This is done by using a multi-stage pendulum system which attenuates the ground motion by 7 orders of magnitude. Even this is not sufficient, so what you really do is put this on an actively controlled seismic isolation platform which provides another 3 orders of magnitude isolation. So the important point is that today, 100 years after Einstein predicted gravitational waves, we have access to the technology to make this measurement. Again, this is a system where if there is gas inside, there will be problems, again there will be scatter. So this huge system, which is 4 kilometers long, has to be put in a vacuum system. The vacuum requirements are ultra high vacuum, etc. So you can see that on a large structure and at the level of the optics, you are really talking about technology which is only accessible today. Again, as Ajit pointed out, you have these 2 observatories. So using them, we can make sure that the disturbance we see in the detector is not because of environment. We have a lot of physical environmental monitors which include seismometers, accelerometers, microphones, magnetometers, radio receivers, weather sensors, power line monitors, cosmic ray detectors, so that you make sure that the signal which you see is not due to any one of these particular causes. Again, when you think of it as a control system, again it's a very complicated control system. So what I want to point out is that this particular experiment involves high level engineering, and essentially almost half the team in advanced LIGO really consists of engineers. So this is an opportunity not just for physicists but also for engineers. So this is the advanced LIGO instrument which made this particular discovery, and as I told you, for the first time we have an instrument which really measured displacement which is 200th of the proton radius. So it is not an exaggeration to say that this is really the most sensitive instrument on the earth, and it has come into being because there is a group of the most talented instrument builders on the planet. Therefore, starting from this detector, advanced LIGO, which made this detection in this observation run, which is called the first run. Now currently we are going through what is called the second run of these LIGO detectors, which will happen for about 6 months, and eventually by 2019 we will get to what is called as the design sensitivity, which will be about 3 times more sensitive than the detectors which we have today. Do we stop there? No, because we basically have the initial detectors which we had, which is shown here by this red thing here. But then, as I told you, in 4 or 5 years we would go to design sensitivity, but we will not stop there. We basically will try to upgrade the instruments, and with the technology which we have today, maybe we can make it more sensitive by a factor of 2. If you really want to go for a factor of 10 improvement, you really will need to invest in R&D related to the next generation detectors, and that is where there is a scope for communities other than the gravity wave community, astronomy community, to make the contributions. For example, as I told you, it involves work in lasers, it involves work in actually building test masses in terms of coatings. So there are many other aspects completely unrelated to mechanical, the gravitational wave astronomy which is involved. So it's an invitation to the whole community to get in touch with us and participate in this exciting endeavor. what we really will do with this is the next generation science, which will allow us to study gravity in its extreme manifestation, matter in its extreme states of, like neutron star matter, etc., and finally allow us to look at the cosmic history, as Professor Kip Thorne pointed out. I end by basically telling you that there are innovations in areas very different. For example, lasers, optics, metrology, vacuum technology, chemical bounding, software algorithm development, which has really happened because they have used techniques which were invented by LIGO, and these techniques have really gone beyond the gravity wave detection. And therefore, gravity wave science has really has had impact on the technology development and invention much beyond astronomy, astrophysics, and basic physics. And this is what I really wanted to share with this particular audience. And this is not just a thing on paper. LIGO technology, by the standard varieties by which technology goes from fundamental physics to industry, that has really already happened. The experiment is really, as I told you, such a marvel of engineering that this experiment really received last year what is called as the Engineering Excellence Award, and it really recognizes all the achievements which this team really has achieved over the last, let's say, 20 years. So I just end by a quote by Beverly Berger, who basically said that every single technology they are touching, they are pushing, and there's a lot of different technologies they are touching. So I end by this last slide, which we basically show whenever we talk about the LIGO India project. So as I explained to you, in addition to all the basic physics, all the basic astronomy, which is all cutting edge, there is this technology interface, and therefore it's not just about fundamental science, it's about applied technology, it's about high-end computing, it's about future astronomy, and therefore I hope I have convinced you that it is an appropriate topic for this particular science congress, which is devoted to science and technology for national development. Thank you. So as I said, we will take questions after this particular presentation, the last presentation by Sanjeet Mitra. So before Sanjeet comes in, you can just get it up. Let me just introduce Sanjeet to you. Sanjeet is a faculty member at the Ayuka Center. His research career has focused on extracting precision science on two frontier research areas, because he was also involved in the Planck projects, which studies the cosmic microwave background, and currently he is involved in the LIGO project. Sanjeet works on other aspects, for example, looking at the stochastic background and so on, and he's like all of us, the member of the Indigo Consortium and member of the LIGO Scientific Collaboration. So let me give Sanjeet to you. So you talk on it. Yeah. After the session, you are coming here. So I will wait for you to come on the stage. I just get here. We will put the question.
Okay. Is it? Hello everyone. So from the last two talks, you learned how gravitational waves were predicted by Einstein's theory, and how complicated it was to detect, but still we managed to detect it. And that was a big achievement, and as you know, it got a lot of recognition from various fronts, and especially also from public media. So in this lecture, I am going to give you glimpses of what are the signs that we are expecting in the timescales of few years to few decades, and how Indian scientists have been contributing to this effort from the beginning, and what potential we have to contribute in the longer run. And of course, there will be LIGO India. So this is just to summarize the picture, that what was detected and announced earlier last year was the merger of two black holes, and which formed a bigger black hole. And the signals in red and blue were detected in two detectors in the US, separated by 3,000 kilometers. So the chances are almost zero that this was generated by some other kind of fluctuation. Now, Indian scientists have been involved in predicting the signal, the first part of the signal and the last part of the signal everywhere. In the central part where it involves numerical relativity, which was a more recent thing, how to use this predicted signal to extract, to make a detection from extremely noisy data, and how to, and lately, how to improve the instruments to get better and better sensitivity. In all the aspects of the detection, Indian scientists have made significant contributions now. And that is a big achievement, but we don't stop there. This is just the beginning, and it will go on. So first, let me introduce some of the science aspects that what we are going to do in the next few years. So although we have detected the black holes, and as Ajit mentioned that the black hole masses were more than what people generally expect, we have very little idea about how these black holes formed. Okay? There are several possibilities, but we are unable to say at this point that how exactly they form. And are all the black holes in the universe very massive? Or it was just a selection bias that we detected a massive one, or just a statistical fluke? Okay? Then what are the distribution of their masses, of the masses of these black holes and their spins? How are they spatially distributed, say in angles and in redshift? So then coming to the neutron stars, that how massive they can be before they merge into collapse to a black hole. These are all very interesting questions. If you read about astronomy, then you know that these questions are very intriguing, and none of these questions have any complete answer right now. And then do more massive black holes exist? So to address these questions, we will need many detections, and that we hope will happen in the coming months to years. Because as you know, the second observing run of LIGO has already started. In the last observing run, which lasted for 4 months, we had 2 detections and 1 candidate, which we could not detect because we did not have enough control on the noise. So the detection, as Ajit again mentioned, opens up the possibility of probing Einstein's general relativity. Is that at which limit the theory breaks? Previous to the gravity of discovery, we did not have a strong handle in the strong field regime of general relativity, where it really differs from Newtonian gravity. And one can basically find deviations, parameterize the deviations of this theory in different terms of mass and spin, and try to constrain it and see that whether the prediction from general relativity falls within these error circles which we derive from the data. If one of these crosses, which are general relativity predictions, were outside this region, then we would say that general relativity needs corrections. This was one of the major things which was done in ICTS TIFR, CMI Chennai, and so on. And then, as I said, Indian groups have been playing major roles in these efforts, like 2 different kinds of tests were conducted, and then when the detection was done, people are involved heavily in interpretation of the data, and several other tests have been planned in the coming years, which will be done with the latest data. Then we can learn about neutron stars also. As you know, they are the densest visible objects on the sky, visible in electromagnetic waves. And then we do not have much understanding of neutron stars, even though they are so exotic and interesting objects. They are basically soup of neutrons. When the neutron stars merge with another neutron star or a black hole, because of the strong gravity nearby, they basically get tormented near the end. And how much they will be tormented depends on the stiffness of these stars. And the stiffness in turn depends on the nuclear interactions. So if we can detect, probe the equation of state, for example, then we would be able to have more understanding of the neutron stars. And depending on the stiffness, the final part of the waves, you don't have to really look at the plots. Just what I'm saying is that basically the last part of the wave gets distorted depending on how stiff the star is. It either gets, if it is soft, if they're soft, then they just merge into form a black hole. If they are stiff, then they go around for a while before merging. Okay. Yeah. Then we come to some of the detection challenges. Even though we have detected a source which was really bright and so on, it is not an easy thing to detect. For example, when since the data is noisy, we need the exact waveform in order to extract it from the noise. Getting the exact waveform means solving Einstein's equation. When two objects are far away, they are just going around each other at a distance like planets do, then it is sort of relatively easy to tackle this problem analytically. But when they are merging, that process is extremely violent and it is not analytically tractable. You need to impose numerical relativity. And that is the time when most of the energy is emitted. Now, a typical numerical relativity waveform that is solving one set of equations takes 2 weeks on 1,000 cores. I mean, this number is of course an approximate number. So you can see how large it is, and we need 250,000 templates to actually cover the whole parameter space. So this could not be done simply by numerical relativity, because I think the total computation power available to the scientific community is not enough. So it required some kind of interpolation, a complicated method which Ajit has been involved in for a long time. These were the things which were used for the present detection. Then extraction of the signal, even after the template bank is created, is complicated because of noise in the data, and it creates different kinds of false alarms. For example, if there is just noise and you are doing match filtering, this is the term which is used generally to find the signal, you will get all sorts of noisy glitches. How do you take that into account? And then the computation cost, because of all these complications, increase exponentially. It is very, very hard to do a full search with all the parameters at present. We do not have enough computation power. So we have to come up with analytical algorithms which can be used to extract the signals efficiently. And at IUCAA, for about 20 years, this research has been done, how to extract data, a signal, a pattern from noisy data. And this was one of the key elements which was used to get the detection. But then it does not stop there. There is a lot more which is going on right now to, for example, incorporate data from multiple detectors to go to higher dimensions. That means, can we use spin parameters also for the search? Right now we cannot because of the computational limitations. The parameter estimation, after you detected, you have to say what are the masses of the black holes and the spins. This is also a challenging problem because the parameter space can be degenerate. That means it is long, many combinations of these masses and spin can fit the data, and then there can be local maxima and so on. So there are groups in IISER Kolkata and so on, they are trying to develop algorithms which can extract the exact parameter more efficiently. So then the other part I said that, when we search for different patterns in the data with different parameters, one or few would correspond to the real signal. Most of the other 2,000 and 250,000 would correspond to wrong signal, wrong values. So you have to somehow say that which one is right and which one is wrong. One of the major problems that arises is because of the glitches in the data, instrumental artifacts. Okay? So there are different algorithms which one can put to isolate them. Not necessarily throwing away the data, but isolate parameter spaces which needs to be searched for the real signal, and rest of it can be thrown away. And then if we can identify the glitches beforehand, then we would be able to even extract it at some point. Okay? So recently we used, let's say, machine learning techniques and got very good results. So I'm not getting into the details of this, just giving you flavors of how, what are the challenges now and how Indian groups are contributing to it. Now I'll come to the later part that I said that there are different things which we don't know about the black holes. So one of the things, fundamental things that we do not know about this merger which was detected is where it is on the sky. And this is because we had only 2 detectors operating at that point when this merger happened. And if you are familiar with the GPS technology, for example, you know that when there are 2 detectors, you can localize something on a ring on the sky. Okay? And that is exactly what has happened for the LIGO detectors. So Ajit already showed this pattern on the sky, which is the error circle for LIGO. It is almost like you can fit in 2,000 moons on this. It is so big on the sky. And it is essentially a ring, but since the detectors were not omnidirectional, there is a part of the ring which you see. Essentially you can see it is almost like a ring on the sky. Now, imagine the hypothetical situation that a detector in India, LIGO India, was operating when the detection was done. Then the error circle would become, would become this small. That small orange patch you see, that is like almost 100 times smaller than the actual patch. So that would significantly improve the accuracy of detection, like 3 GPS satellites do. And that is one of the major motivation for LIGO India. And we not only 3, we actually need a network of detectors across the globe. This is because the detectors are not working most of the time, not all the time. So at least 20% of the time detectors are down for upgrades and so on. Okay? But for every detection you want at least 3 to be present. So if you multiply this probability 0.8 into 3, 0.8 into 0.8 into 0.8, you see the probability significantly drops to some 60% or something. So you need 4 or 5 detectors to be operating for every source to be located on the sky. And then because of other geographical reasons which I am coming to, India is a very good place to host a detector. So the thing is that, so right now we had 2 detectors in the US. This is the map of the world seen from the pole, North Pole. Okay, you see there is this H and L. These are Hanford and Livingston detectors, okay, which operated for the detection. And then there is a Virgo detector coming up in Italy. Virgo detector is already there, but it will start operating at the advanced configuration probably later this year. So that is marked by V. Now if you put a detector in India, you see the baseline distance. That is the light travel time between the detectors increase significantly, and also the number of baselines double. That gives you a large network to accurately determine the position on the position of an event on the sky. Okay? So this is one of the big motivations for LIGO India, but there are more. Okay? So basically this is a plot which were pretty popular. So on the left side, on the upper left side, you see the error circles on the sky with the LIGO and Virgo detectors, and they are pretty big. But when you have LIGO India, then the error circles reduce significantly. And then the duty cycle improves. That means at least 3 detectors working at a given time increase. That the sky is uniformly sampled also improve, because the detectors see some directions better than the other, or those non-uniformities sort of get sorted out because of all this. And most importantly, for from the Indian perspective, Bala already showed you this slide, that a detector in India will give significant opportunity to Indian experimentalists to get involved in cutting edge science within a mega science project. So people would be exchanging knowledge, and this will give us a platform to go beyond. LIGO India is not the end of the story. It is just the beginning again from the experimental point of view. And I will show you a little more things later on, that what else the people have started working on already in the international community. And hopefully after LIGO India, the Indian community would be able to contribute to those efforts. Okay, and government of course recognized it, and there was quite a bit of support from the top level to move LIGO India pretty fast, and you can see that Prime Minister himself was involved in many of the meetings where MOUs and things like that were signed. So what is the status right now? My institute IUCA led the site selection activity. 39 sites were followed, and then some of them were shortlisted. Right now there is a primary and alternative site which has been recommended for LIGO India, and several surveys are going on at the site. You can see that the lower bottom plot shows the terrain map which was obtained from ISRO. So if for one of the sites, and these are the kind of details we already have. Then there was a tier 2 data center which was set up at IUCAA. It is one of the major Indian contributions to the international gravity wave community. So the gravity wave community is always looking for computation power because the searches cannot be done right now with limited computers, and this will serve a fraction of that. There are several details involved, but the important thing to notice is that the facility is being used by gravity wave community from India and abroad. And also we have a building infrastructure ready for a bigger data center, the tier 1 center, which will be needed for LIGO India operations. The next thing is coordinated Indian follow-up of gravitational wave events. We would, if we can see one gravity wave event, let's say a neutron star merger, in gravitational waves as well as electromagnetic observatories, we will have far more understanding of those systems which were almost unknown at this point. So there is a dedicated 70 centimeter telescope which would be installed, which will be functional, actually operational later this year. This effort was mostly led by Varun Bhalerao at IUCAA and IIA. IUCAA, then also the existing observatories in India can sign up for follow-up program with LIGO. The IUCAA has a 2-meter telescope which has signed up, and then AstroSat, the CZTI instrument, has also signed up for such follow-ups. So, but then there is activities going on to encourage Indian astronomy community to sign up for such follow-up events. It takes a small fraction of telescope time, but the returns are pretty good. This is called the target of opportunity observations, and that is going on. And then also there are plans for dedicated telescopes for future time domain astronomy, so-called. Yeah. And then of course the astronomy community, to encourage the astronomy community, several sessions were organized in the Astronomical Society of India meetings in the last 2 years. So here is a list of activities for LIGO India right now. So the MOU between DAE, DST and NSF has been signed on March 31st, 2016 in the presence of the Prime Minister. Then key project management structures have been set up for LIGO India from the top level. LIGO India site selection process has recommended a primary site, and the site acquisition and development plans are getting initiated. Then of course the detector is going to come from, some components are going to come from the US, but we have to build a 4-kilometer long vacuum, okay? It is not an easy thing. So there is a lot of effort going on to do that. Even after you get the instrument, there's a laser, the suspension system, just to install them it's pretty challenging thing, okay? If I just give you a broken laptop, I don't think you will be able to fix it so easily. This is just a joke, of course. It is much more complicated in that case. So first to get the instruments, assemble it, understand the noise characteristic of that, these are all very complicated. And not everything is going to come just like that. For example, the suspension system has to be done in India because we need cables which are basically silicon, basically glass, which would be holding the 40-kilogram mirrors, okay? This is done by, if you have seen how the glass is heated and the bubbles are made and so on, it is a much more, of course, sophisticated version of that. You put a laser and then pull the glass, and then you get a very narrow thread which would hold these heavy mirrors. This thing has to be done in India. And there are several aspects for that. Preparations have been started, okay, to train people, get some equipment and so on. In IPR and RRCAT, these operations are going on for vacuum and laser. And also there is progress on data center front. And last but not the least, so as I said, LIGO India is just the beginning. We don't want to just install the LIGO India like that at advanced LIGO sensitivity and then stop there. We want to upgrade the instrument as the other instruments in the world are being upgraded. We want to get involved in the future activities. For that, we need to build a big experimental community. There has been a series of meetings which is being organized at IUCAA, and the response are overwhelming. There are 40 participants in 2 major meetings from 20 institutions, okay? They are signing up for different tasks. which are there. I mean, I cannot get into the details of what exactly is necessary. I will show one example later on. And then people would be basically taking up those tasks, work with the international community and deliver the results. And this will be one of the key steps towards building the experimental community. So there is enormous enthusiasm all around to take part in LIGO India and go beyond. So one of the examples, as I said, I will give is about Newtonian noise, because I am involved in that. So you know, when we are trying to detect, measure distances between the mirrors at the effective precision of which is less than the size of a proton. It is like that small. So any vibration can shake things up, right? Now there is, the mirrors are hanging from a platform. The platform is on the ground. There are several layers of passive and active isolation which keeps the mirror from not moving because of seismic vibration. And that has worked so far pretty well, even though we want to move beyond improve the lower frequency sensitivity, which is limited by the seismic isolation. But then there is gravity. When a wave is passing by, if you see the image, you can stop the vibration on these suspensions. But each of these matter perturbations is directly coupled to the mirror through gravitational coupling, right? This is the Newton's law. That is going to create a tiny perturbation in the mirror, which will also become important in the next generation detectors. So we have to somehow get rid of this noise. But how would you do that? You cannot isolate gravity by anything. There is no Faraday cage of easy sort. So what we have to do is to put an array of seismometers on the ground, get this noise, and we know that this noise is going to be correlated with the effect on these mirrors. So we pass it through some adaptive noise cancellation techniques and we will be able to remove it. Right now we have no idea, we cannot measure this noise, so we don't know how strong it is also. But we hope that this kind of schemes will work. And this is a huge amount of task, because even to estimate how much noise is there, you need to understand where to put the seismometers. That is like a iterative business. So these things we are already part of, and hopefully some things will come up. So up to this, so why we want to do this? For example, we want to improve the low frequency sensitivity. Why? Because the binaries which are merging spend most of the time in the low frequencies, because you know, when they are far away, they are slower, the rate of merging is slower. So if we can monitor that part very carefully, then the masses can be determined to very high accuracy, which will help us in testing general relativity, for example. Okay. So, but all these things I am saying were mostly I have been focused on the binary detection and the parameter estimation and so on. But being a new field of astronomy, we also need to see how we are going to find the unknowns. Okay? For unknowns, by definition, we don't know the phase. We have to rely on techniques which will use our very good knowledge of the instrument and see if there is some excess power coming from some place. Okay? So I will talk about two different things here, short-term and long-term unknown signals. How do we probe them? So one of the things is bird searches. So the binaries, when two black holes merge, they create huge amount of, they emit huge amount of power in a very short duration. Okay? That is also a burst source. But since we know the waveform very well, there are more optimal methods. But suppose we did not know the waveform. We did not know how the waveform looks like, or our understanding is wrong. That even though we think this is the waveform, it was not the case. Then how do we detect them? So we create this kind of time frequency plots. This is time and this is frequency, and what is plotted is power the strength of this color is power. So and then we see whether the same thing occurred in two detectors separated by 3000 kilometers and more, in fact in a network of detectors. If every detector gets a small excess power of a certain pattern in the time frequency curve, then we can be very confident that this is probably something of gravitational origin, but we don't know the exact signal. Okay? And that will be one of the ways to probe the unknowns. And groups at ISA Trivandrum are involved in this. In fact, this analysis is pretty fast. The first detection when the first black hole merger was actually detected first by this pipeline, and that was in 3 minutes. Okay? Because it was pretty strong, but it was not true for the other ones, because this kind of searches work when there is a burst of power, not when the power is distributed over a longer time. Now the other method which I work pretty heavily is for unknown sources which are persistent. Most of the astronomy is actually about those sources, electromagnetic astronomy. For example, when you see a star, you don't know the phase of the electromagnetic waves which are coming from the star, but you know that there is a constant amount of power statistically there in the star. Okay? So how to look for those sources? Basically what you do is to correlate data between two detectors and try to see if there is a power excess, because even though the source is random, the same signal is coming in two detectors. So when you correlate, there will be a peak, a small excess in the correlation when there is a signal, versus if you, for example, time shift the data by unphysical amount, those correlations would not be there. So this is how we try to figure out if there is a long-term excess in the data, and plus you can use this method to make a sky map also. I will not get into the details, but these are kind of like Earth rotation synthesis imaging which is done in radio astronomy like in GMRT. And then Ajit already mentioned that this method will be very useful in getting, in probing the history of black hole formation, that how the binaries form. There are several models and we cannot pinpoint right now, but if we integrate throughout the history of the universe, different models predict different background, confusion noise, okay? And that is order of magnitude different when you do this theoretical estimation. So if we can, in addition to detecting the individual sources, if we can also detect a stochastic background like this, we will be able to have much more control on the much more better understanding of how the black holes form in the universe. Are there only one channel or two channels? Different formation scenario. Do they form in isolated regions or do they form in, let's say, dense star cluster environment? All those kind of things. If they form in two different regions, is there any qualitative difference between them? And these kind of things. And hopefully in the next 5 years of advanced LIGO operation, we will be able to detect a signal like that, if our optimal understanding of the average model is correct. Okay, I'll finish in like a few minutes now. Now, getting into slightly distant future. So you see that the final aim, a major aim, is to understand the universe, how it originated and so on. So we have this Big Bang model, which was, it is not just the Big Bang, it has lot of details. This model was formed after several years of understanding of observational cosmology. And we have a self-consistent model right now. But there is a phase in this model, in the very early stage, when the universe had to expand exponentially, and a significant amount of expansion happened during that time. This is called cosmic inflation. That phase we have to put in by hand in order to explain the data. And we want to see that phase. There is no way you can see that part in electromagnetic waves, because the universe was so hot and dense that photons could not travel straight at that time. Photons became relatively free when the universe was 400,000 years old, okay, which created the cosmic microwave, which is the cosmic microwave background. But 400,000, the inflation happened in the first second of the universe. So we have to use some other means. So there are two ways to see that. One is gravitational waves and other is neutrinos, which can penetrate this dense environment and come to us, okay. And there is a lot of effort going on to see the first, that signal, primordial gravitational waves. And I don't know if you can read this plot. Basically there is a frequency axis, a horizontal axis frequency. It goes in orders of magnitude. Basically in different bands, people are developing instruments to see, to probe this background. And not only that, so even though the chances of detection of that background with the existing instruments is fairly low, there is enormous amount of effort going on to develop next generation detectors. I mean, this may sound like fantasies, like these are, the names are like this: Primordial Inflation Explorer, Big Bang Observer, then Deciharge Interferometer Gravitational Wave Observatory. But the thing is that, and these have enormous sensitivity. I will show you a plot, landscape plot, to show where things stand. The thing is that even though these things sound too futuristic, the work for this have already begun. All the pictures which have the designs and so on are from scientific papers and documents. So it is, even though it is futuristic, we have to start almost now in order to catch up.
For LIGO, it took 30 years of effort before a detection could be made. Okay? So futuristic does not mean there is no work now. It has to start right away. For example, this is the next generation gravity wave detector. It's called the Einstein telescope. Okay? The designs are being finalized, but site surveys have been done all over the Europe to find a good suitable site. This will be an underground telescope which will be like 100 to 200 meter underground, and the arm length could be 10 kilometers. So these are not finalized things. But on the other hand, efforts are going on heavily on each of these aspects. Then there is the laser interferometric space antennas called LISA. So because of funding situations, the LISA's launch date keeps fluctuating, but this has enormous amount of the science case is enormous. We would be able to see, okay, let me play this thing. So what is proposed is that 3 spacecrafts will follow the Earth and exchange light, laser light. And then by measuring the Doppler effect, we would be able to detect supermassive black holes. Okay? It is believed that supermassive black holes are there at the center of the galaxies, and smaller black holes are falling into it. They are going around it and at some point merging. So those things we would be able to see with this. And again, this is not a science fiction. So there was enormous success with what is called the LISA Pathfinder mission. The results came last year. So the Pathfinder mission checked some of the key technologies which will be used for LISA, and there were some set goals that if Pathfinder noise capabilities reach this level, then we would think that it is good for LISA. LISA is physically possible, practically possible, and it did 10 times better. The noise level of LISA Pathfinder was 10 times better than what was projected. So this is at that level. So I hope that LISA will fly soon, definitely much before I retire. Okay, so this is the sort of landscape of gravity wave detectors and sources. I don't think you can see it, but just to say that everywhere there is effort going on, and we are right now only near the audible frequency range, but the detectors are being built all over. So, okay, so this is my summary slide. So I will just read through. So the first detection marks the beginning of gravitational wave astronomy. Detection of large number of compact binaries promise interesting signs like the distribution of black holes, neutron star signs, etc., etc. And we hope that many of the detections will happen this year after in the second observing run of LIGO. And worldwide effort is going on to improve the sensitivities of the detector, build a network of detector, and so on. LIGO India activities are also taking shape pretty rapidly, and Indian community is ready to work on LIGO India to contribute to it and taking it beyond. And much more excitement is expected in the coming decades. So I stop here. Okay, and while people are coming, so this is the spectrum, and we are just at one frequency on the right side right now, and all these things are being planned.
So now we open the session to questions. Since we have short of time, I would actually, give the chance to younger people. So come forward, use the mic, and then answer the question. Ask your question.
Yeah, I am Dr. Vinod Kumar from ISRO. As previous presenter has said that 3 satellites is required to find those waves, LISA satellites. At what altitude you are planning them? What is the height, where they should be placed? LISA satellites.
Oh, the orbit?
Yeah.
Yeah, so LISA is basically the arm length for LISA, which was initially proposed, was I think 5 million kilometers.
Or are there Lagrange's points?
Where is it?
Yeah.
Okay, fine.
Yeah.
Good morning, sir. Thank you for the wonderful presentation. My name is Vishnu, and my doubt is, we know that the expansion of universe is accelerating due to dark energy. Then what happened to the gravitational waves due to the Big Bang, which was probably billions of times more powerful than two merging black holes? And also that occurred at a time when the universe expansion rate was very less than at the time of those two black holes merging occurred. Sir, I will repeat. So we know that the expansion of universe is accelerating due to dark energy. Then what happened to the gravitational waves due to the Big Bang, which was probably billions of times more powerful than two merging black holes? And also that occurred at a time when the universe expansion rate was very less than at the time of those two black holes merging.
Yeah. So the thing is that the dark energy's effect, that acceleration, is more pronounced in the present time. At that time, there was inflation happened for a short while in the universe when the universe accelerated a lot. The primordial gravitational wave was generated at that time during that inflation, that rapid expansion. So there are quantum fluctuations which were suddenly, so I think since you are interested, so if there is a quantum harmonic oscillator in certain ground state and you suddenly change the potential, okay, it can go to excited states. And that is one of the theories which says that how the gravitational waves were generated in the early universe. And the second question you were saying is that when the black holes, the ones which were detected were so close that the effect of dark energy was not much, in the sense that the acceleration of the universe creates a change in the distance in measurement when the object is far away. That is, the redshift is more than or comparable to 1. The one which we have detected is not that far away. So, yeah.
But the expansion should be very high in case of that merging black hole, so it should be diluted. No?
It is marginally, it is very small, because the thing is that the redshift is 0.1, it is very close. So it would not have very significant effect on the, so on the other hand, turning around, when we start seeing objects which are far away, the effect of dark energy will be on those sources, will change those, the signal which we receive, and that can be used to probe dark energy. Okay, that is one of the science goals of this system. Of course, we don't know how much we will be successful.
Yeah. Sir, you said that we have to go to the great extent in order to detect the gravitational waves, so that we can make sure that the gravitational waves are nothing else like interstellar dust and seismic noise. Sir, can we build an underground gravitational wave detector with cryogenic mirrors so that the thermal noise and the seismic noise are reduced to great extent?
Well, there is there is a detector which is coming up in Japan, which is using cryogenic detector. That is, the mirrors will be cooled so that the noise level goes down. But this is a technology which is being tested. We don't know how far it will improve. The hopes are very high. And then hopefully probably in the next generation detectors, this will be the standard, that people will use cryogenic cooling basically to reduce the Brownian motion.
Yeah, thank you.
Sir,
Good morning.
Good morning, sir. My question is that what is future possibilities to communicate with gravitational wave? Or can in future it is possible to communication with using gravitational waves?
Communication with gravitational waves?
Yes, sir.
It is, so for a communication device, you need to generate a signal and receive it, right? Generation of gravitational waves in a earth-based system sounds very, I think, optimistic. I don't know if we will be able to generate gravitational waves to do that.
It's an issue of detection, right? Because it's easy to generate gravitational waves. If you move your hand, you are generating gravitational waves. Any motion of massive object produces gravitational waves. But the problem is that they are very, very weak. So if you want to create a detector that can detect gravitational waves produced by small motions, you need to go to several orders of magnitude, like 10 to the minus 50, which is not possible using any conceivable technology right now. that's conceivable right now, but in the future you might find some better technology that you can detect gravitational waves of 10 to the minus 50. But you don't know anything yet.
Sir, because at Einstein prediction, they already told that detection of gravitational wave is already not possible. But till now,
Can you hold your mic close?
sir, Einstein predict that the detection of gravitational wave is already also not possible. But till now, we detect gravitational wave, so it is in future. It is possible.
It might be. So Einstein did not know what kind of technology that would exist after 100 years, which made the detection possible. So we also don't know what kind of technology become possible after 50 years or 100 years. So it might become possible in the future. We don't know.
Thank you,
And
sir.
also the thing is that, there is, even if we do some kind of motion in the lab, there is 1,000 kinds of things happening in the earth, and we have no control on that, right? So the chances would be small.
Good morning, sir. My name is Satish Vaji Patel. Now day on day the gravitational phenomenon was getting clear idea about its nature. So what is effect on the mass energy equation is equal to mc square, whether it changes or as it is?
No change. There is no distinction between mass and energy in Einstein's theory. So what we call mass is, you can call it energy as well.
Sir, because the speed of waves is more than light, then it will obviously cause to change the equation. So that is to be possible, sir.
Right. So according to theory, the gravitational waves travel precisely at the equation of the speed of light. But we do experimentally try to test whether they are indeed traveling at the speed of light.
Okay, thank you, sir.
Sir, I have two questions. My name is Faraz. First one is, how can we so sure the first wave we detected in 2015 was created by merging of two black holes rather than merging of two neutron star or anything else?
So essentially what we do is compare the data with theoretical predictions of Einstein's theory by solving Einstein's equation for various assumed masses. So Sanjay told you that we compare the data with about 200 million templates, and these all correspond to different masses. So the expected signal from a binary neutron star looks very different from an expected signal from a binary black hole. That's why we know that these are from black holes.
Sir, I attended the Nobel Prize winner Kipson lecture also. He said that what Einstein said about gravitational wave was not so correct. Later on it was said. He showed it in some slides.
No, at some point Einstein had doubts whether the gravitational waves were physical phenomena or not. And this was settled after a lot of mathematical work and something Bala Iyer mentioned about Bondi, Sass, etc.
So second question is, in the last part it was said that gravitational wave will help us to find the origin of universe or Big Bang. If these are waves and it just spread out after the universe in just after first second after the Big Bang, how can we detect it after so long time when Earth is created, matter are created?
Are you asking that how could we detect the waves generated during Big Bang?
Big Bang, yeah.
Now?
Yeah.
Yeah, because the universe is probably infinite. So when you are receiving a light at this point, it was generated at some other time. Okay. Now if the universe is infinite, then at every moment you are receiving something which was slightly further away. For example, as we are speaking, some waves are passing through us. 1 hour later, something will again pass through us which was created 1 hour before. Okay, and it is going on like that. So, and since or in the sense that it is distant. So what I mean is that you have to visualize it. Let's consider an infinite universe where things, some waves started moving. Okay, and they will always keep coming to you, no matter when you, where you are.
So if it was started, then it would have passed us now.
Some have passed, but the thing is that let's say that you consider a point which is, let's say, 1 light year away.
Yeah.
That if something happens there, that will pass you after 1 light year.
Yeah.
But then consider another event which has happened 2 light years away. That will pass through you 1 year later.
So, but
And now
Big Bang is only once now.
No, but it is everywhere, right? So now we consider an array of this. Let's say that something happened now, everywhere something happened.
But then it is the concept of parallel universe. Many Big Bang is there.
No. There is only one universe. Only one thing happened at once everywhere, right? So, and since it is infinite, you just think about it. A spherical shells are collapsing. So each moment, one sphere is going to collapse here, or in the other, on other, yeah. Okay, okay, yeah. You think about it.
No, no,
welcome.
I would request you to wait. I would like to give the students the chance. We can talk after the session, please.
Sir,
No, no, please.
sir, I would like to ask two questions. The first one is, what is the event horizon? And the second one is, how the wormholes or Einstein-Rosen bridges are formed. Can these detection give answers to these questions?
Okay, so event horizon means, as Ajit pointed out, when you have a gravitational field, the propagation of light waves or any radiation is affected by the presence of the gravitational field. So when a gravitational field is very strong, then there are regions of space-time from which nothing can come to you. So therefore you say that surface which separates the events which you can see from events which you cannot see, that surface, imaginary surface, is what you call as the event horizon. Wormholes are specific solutions of Einstein's equations, mathematical solutions of Einstein's equations. But if you try to use some physical matter to create these wormholes, as of now, today we cannot really create these objects. So currently mathematical solutions of Einstein's wormholes are mathematical solutions which allow you to do many wonderful things, but physically we cannot create one by using the physics which we know today.
Sir, another one question.
No, no. Give
Thank
answer.
Hello, my name is Rushikesh. You are told that the signal was detected, and then we extrapolated, and then we said that the gravitational waves were formed due to the merger of two black holes, and then we predicted the masses and velocities of the black holes. But those predictions were based on Einstein's theory. So how can we be confident that the theory is so perfect and the predictions are so right?
Right, so strictly speaking, all we can say is that our data is fully consistent with Einstein's theory, because in science you can never prove something is wrong. You can always try to disprove something. So we always try to disprove Einstein, but we manage not to do that. So the data is so far consistent with Einstein's theory. But if we see something that is inconsistent with Einstein's theory, that would mean that we will have to revise Einstein's theory. But so far we don't see any evidence of Einstein's theory breaking.
Thank you.
Sir, you talked about a 4-kilometer vacuum tunnel will be made, but for what purpose will it be made?
Well, if there is, you saw that picture, the animation, that lasers are going to hit the mirrors and come back, right? And there is enormous amount of laser power which has to be built up in these cavities. Now, if there is gas inside, then there will be too much of scattering, right? Which will create unintended radiation inside and reduce the power. So we need to get rid of the gas so that it is mostly vacuum.
Okay. And sir, if anything enters a black hole, then where does it goes out from? Where does it go then afterwards?
Nothing can come out of black holes. So what we see is when two black holes are going around, the gravitational waves are not generated, are not coming from within the event horizon. They are coming from outside, the surroundings.
So we can predict that even universe has an output, some also after universe, is there anything outside the black hole?
Are you asking if there is anything outside the universe?
Yes, like if we have a room, if we go out of the door, we enter into the next room. So after the black hole, where do we go?
Oh, okay, so you are talking about complicated topologies of the universe where you go from one side and it is like a donut shape, let's say.
Yes.
This kind of things?
Yes.
Well, those definitely happen in movies, but I am not sure whether in real life, it is not impossible. See, these are complicated topologies of universe is possible. Like, for example, the universe is a donut, and then there is a connection somehow where you go through and so on. But I am not sure. These are all speculative.
Okay. And sir, if two wormholes...
Give some chance to somebody else, please.
Sir, is this any scope for generating electricity from gravitational waves, sir?
generating electricity from
Electricity. Oh, that chances would be very, very small. Because the gravity is a very weak force. It does not couple too much with matter. So the chances are that if you produce huge amount of gravitational wave spending huge amount of energy, the amount that can be converted to electromagnetic energy would be very small.
As Saad said, it's 10 to the power of 48 watts per day. It's impossible.
For that, I think you need black holes to capture that much energy, a black hole in your backyard, but that is not possible.
Okay, thank you, sir.
Good morning, sir. Is there any possibility of merging of gravitational waves from two different celestial objects?
Yeah, it is possible. You know, if you have two sources merging at the similar distances and producing signals, and they arrive at the same time and interfere.
I mean, like gravitational wave from sun and gravitational wave from black hole.
They can interfere, but the problem is that usually, you know, when one of them is significantly stronger than the other, then the stronger one dominates, right? So if you want to have a significant interference, the two waves have to be comparable amplitude, and the probability of that happening is very slow at the moment. But when you get a sensitivity where you see a large fraction of the universe, then the probability of simultaneous signals arriving at the same time is quite significant. Then you will have to worry about only the confusion backgrounds.
If that wave is detected by LIGO, what are the outcomes? I mean, we can't predict the exact object from which the wave came. I mean, if the merged wave is detected by LIGO.
So we'll close the session now because we need to start again.
Yeah, so we have very specific, we can solve Einstein's equations for the case of black holes, and we have very specific solutions, and we have a precise calculation of the expected signal shape, and the data agrees very well with that specific signal shape. That's why we know that these are black holes.
Thank you, sir.
Can you just give?
Sir, mine is a very basic question. Can you detect antimatter using this LIGO experiment? Detect.
Antimatter.
No, I mean, the antimatter also has mass. So if it is, I don't think there will be any difference between matter and antimatter for gravity wave emission.
Anti-gravity.
Oh, anti-gravity, I don't know if there is something like that.
Yeah. Hello, my question is very simple. What is the properties of gravitational wave like other waves like radio waves, electromagnetic waves, light waves? Physical properties of gravitational wave.
They are transverse waves which propagate at the velocity of light.
Yeah.
Basically, when you simplify Einstein's equation, like if you have done electromagnetic theory and you put the right-hand side to 0, that there is no source term, you get a wave equation which you can solve to find the solution, and then you see that the velocity becomes the velocity of light. For gravitational waves also, if you remove the source term, that is no matter energy, it is just free space, and the source is sitting somewhere else, then you will see that it is there is a wave equation where the wave propagates at the velocity of light. There are two polarizations, and they are transverse in the sense that the wave propagates in one direction and the polarization in the transverse direction. Like Ajit showed that if there is a ring of particles, and the gravitational waves are propagating, then there is one which does this, then there is another at 45 degrees which will do this kind of.
Okay, thank you.
Hello, sir. What happens if there is one planet, after it there are other two planets? If they collide and we want to measure or know about the first planet, and if they collapse, then the gravitational force of first one and the second one, second two which collapse, can they get, I mean,
I think Ajit had already answered in the previous thing that if there are two events going on at the same time, the probability is very small, then there is a superposition of the waves.
Yes, sir.
That is there. However, detection of probability of a planet merger is very small right now with the current detectors, and also two planets merging at the same time, the probability would be really, really small.
Good morning, sir. My question is, you said that when two black holes comes near to each other, then they given out the large amount of energy. If there is possibilities to come 3 or more number of black holes come together.
Yes, there are possibilities that higher number of black holes can come close. Let's say more than 2, let's say 3. But these black holes move so rapidly when they are close, that the chances are very high that one gets kicked out of the system very quickly. Okay, like you have seen that how, let's say, spacecraft are moved to another orbit, like using another one's gravity and so on. So when two black holes are going around and a third comes, that is one of these three, not necessarily the third one, can get kicked out very fast, very rapidly. So that three things merging together is almost impossible. Only two will merge.
Can you just give it to her? Yes? Excuse me. Can you just give it to her?
Yeah, excuse me. I congratulate all the speakers for their lucid and thought-provoking presentations. I have one question. Will the seismic waves drastically affect the gravitational waves at the time of earthquakes?
Yes, it does. It actually unlocks the detector many times if there are earthquakes. So there is a there are a lot of suspension systems in the detector in order to isolate the detector from seismic vibrations. So so if you take a pendulum, for example, and then shake the top part, then you will see the pendulum does not move as much when you are moving at high frequency. Okay, so that is like a suspension system. LIGO has a 4-stage, 2, 3, 4-stage pendulums at different places in order to isolate this kind of vibrations. Even then, it is not guaranteed that when there is an earthquake, the system can be stable. So the system becomes unlocked. That means the laser power goes down, and again it has to be brought to the operating situation.
So it's not possible to predict the earthquake using
Not
this
to predict.
gravitational?
You cannot predict it. I mean, it happens after the earthquake has happened.
Okay. Thank you.
No, go ahead. Let them finish. There are two of them only, last two. Please go ahead.
Sure, sir. So my question seems pretty simple. What makes, you said the interferometer can detect a deflection of 1/200 of the diameter of a proton and node. What makes the interferometer so sensitive, extremely sensitive? What's the principle behind it?
Yeah, so what I told you, right? I mean, in my slides, I basically explained to you that starting from a simple interferometer, you try to, which is a few kilometers long, you can increase its optical path length by using these cavities, and then you can improve your fringe sensing if you have more power in the. So putting together all these techniques which I mentioned is what allows you. So it is the different techniques like power recycling, Fabry-Perot cavities, the photo detectors which you use, which can measure very small intensities. All these things put together allow you to measure 10⁻11th of a fringe.
No, sir. That's an extremely sensitive case.
Yeah.
We have in our laboratories as well the interferometer.
Yes.
What's the basic principle behind a simple interferometer which is just a few feet long or a few meters long?
So obviously, the sensitivity will depend on the, the displacement sensitivity will depend on the length which you have. And the main problem is, if you are working on an interferometer, just the fact that, if you just tap it, things will keep moving, etc. So it is the fact that when you have an interferometer, if you want to make it more sensitive, you have to really do all these things, isolate it from all the other noise, which you do by using optics table. But then you have more sensitive things to isolate it from the ground so that other sources of noise are taken away. So it is a combination of all this which makes this instrument as sensitive as required to detect the gravitational wave.
Can I add something?
Yeah.
So the simplest principle is, so in a normal lab, you look for the difference between a dark and bright fringe, right?
Yeah.
So it's like a wavelength.
Yes, sir.
So if you want to do a very precise measurement, you should be able to detect small changes in the bright length, which is a small fraction of from dark to bright. So in LIGO, like a 10 to the 12, a part in 10 to the 12 fraction between the full bright, the full contrast is able to measure by using all these techniques. So you're simply looking for small changes in the output power.
Okay, sir. Is it basically related to the phase difference between the two waves or the amplitude,
The phase,
frequency?
From the
it's
phase
related
you
to the
go
phase,
to the
right?
intensity. Yeah, the phase thing is converted to an intensity, and you can monitor small changes in intensity.
Which is reflected on the pattern.
Yeah.
Yeah. Thank you, sir.
That is what is called, I think, as fringe splitting is what is the technical name for it.
Sir, I'm Bharat from University of Glasgow. I'm pursuing my mechatronics bachelor's first year, and I have a question. We are working on detection of gravitational waves, but at the same time, why don't we work on detection of dark energy too?
Well, you can, right?
So is there any idea or any process going on for dark energy in India as of now?
Yeah, there are other groups, tomorrow there is a session on neutrinos where you would talk about, that particular experiment is also looking for setting up experiments in India for looking for dark energy, for dark matter.
Okay, sir.
So my question appears to be quite simple. You told that the unified mass of the two black holes appears to be less because the remaining mass converts to be the energy. So is it possible for this released energy to recombine at some place for creating new celestial bodies?
No, I didn't understand the question. Do you understand the question?
Can you use this new energy to create new celestial bodies? Is that what you're asking? But in the case of binary black hole mergers, all the energy is converted into gravitational rays, according to our understanding. So I don't think there is any creation of any new celestial body.
Okay.
Welcome. I just would like to welcome your interaction. What is required here is an international community also should understand what the significant aspects of our own Indian knowledge base. Okay. Right from Carl Sagan to Alfred, they started putting the question, and also Indians are not coming up in proper way of comprehension of the entire universe. So I have been putting forward through research reports and also interaction through nuclear plasma, space plasma groups. And the question Salfan has put it is available December 1992, even IEEE. Or 1984, Bangalore also has got the original papers. Now this group basically questions the assumptions on Big Bang and also the black hole to be replaced by a waveguide and then control and regulate function. It's the Indian knowledge has to come up. So what I compiled is like a research reports now available as books. One can click on lulu.com, Cosmology, Vedas, Interlinks. It so happened about 10 years back, I gave a key lecture right at Tirupati. How to interlink with modern science is a big question mark for a lot of universities. This knowledge base has to come up through a different method. That means your base concepts have to be revised, source, fields, flows, leading to protective environment. Protection is the basic also from the Indian science point of view.
Yeah, I think,
Okay.
at this particular
Let
point.
us see that. Now, this base concepts.
No, thank you. I think we will, whoever is interested will go to the Google site.
These base concepts have to be linked to prime concepts. Then only you will understand the knowledge base beyond the Milky Way galactic plane.
No, that is fine.
Okay.
But I am saying
So
that.
welcome anybody is interested. A few books are, I brought it here.
Yeah, sure.
In the evening I am giving a short lecture in the physics department.
Yeah, no.
Nice of you. Thank you very much.
Thank you. So I think with this I close the session. Yeah.
Hello. In disorder system practically, if we measure the fluctuations in time domain, in frequency domain it gives rise to short noise spectrum or Johnson noise or 1/f noise. So what are the frequency domain data? Are all these fluctuations are 1/f noise or short noise or Johnson noise are present here, or how do we eliminate all these things?
These are, this will be like, there are, we did not, of course, show this kind of plots. There is short noise at the high frequencies, at the low frequencies it is seismic noise. In between at the central, the thermal, the sweet spot of the detector, it is all thermal fluctuations, and there Johnson noise is involved. So the thing is that, I think it will be technical, but I'll just say at least one thing, that these mirrors are hung by a string, okay, meaning that a wire which is made of glass. There are thermal properties of that. There are, it has a certain resonance. So, and then there is a certain amount of damping there. So you see that Johnson noise is already there. What we try to do is that we try to move the resonance frequency of this, of the components to either to very low frequency or to very high frequency and increase the quality factor so that most of the energy, this Johnson noise basically, goes to is localized in those frequencies which are not in the detector's band.
So then how do you take care of the effect of aliasing in this case?
These are, generally there is no aliasing will happen in the hardware thing, right? I mean, we are not doing a frequency domain. I mean, it is not a mathematical thing, but we can talk about it. I cannot say exactly how it is done. So for example, like for the meters, etc., the frequencies move to some few megahertz and so on. Yeah.
Okay. Thank you, sir.
Thank you. Thank you for participating in this session. So I declare this section closed.